So the good news is the concepts have all stayed the same. Some of the algorithms and classes have changed over time and some of the techniques, but the focus for the talk will really be about conceptual things. I'm going to show it to you in C# and .NET 6. So I just upgraded to .NET 6 over the weekend and everything went really well. But any language, any framework, you're going to find access to these kinds of classes and these techniques. So even if you're not a C# developer, stick with me and understand the conceptual things. It is a 101. I will mention a couple things that are more advanced, but we want to get the base concepts of how to use cryptography. A little bit about myself so you can read some of the background information. I have my Twitter, my email, and my blog there. And at the end, I will have a link to the slides. I have two versions of the code. So I have .NET 4.8 full framework, and then I also have the .NET 6. I have not yet optimized it for the latest C#, so there's a lot of cool new things in C# that I could do to reduce some of the code size. I haven't done that yet. I just did a build from .NET 5 to .NET 6. I had one warning that I'll talk about as we go through the talk, but otherwise everything moved forward really well. So some background. So cryptography is the science of keeping messages secure. And when you think about cryptography and you talk to average developers, most people will think about confidentiality. So that's one of the major goals. You want to protect the data from being read. But there's also three other good goals. One is integrity. You want to verify that data has not been modified. We use it for authentication to identify and validate a user. It's used for non-repudiation, which just means a sender can't deny later that they sent a message. So we're going to get into digital signatures for that. Again, in .NET, the namespace is system.security.cryptography. That's where we're going to find the classes that I'm going to talk about today. There's a lot of considerations when you step into cryptography. So for instance, starting with what is your goal? So I'm going to tie back techniques throughout the talk back to specific goals. So it's important to know what your goal is will help you realize the right technique to use. I see a lot of people that are using hashing when they should use encryption, or encryption when they should use hashing. So hopefully we'll talk through those goals and we'll look at the techniques and map them back. So if you start with what is it you're trying to do, it'll guide you into what techniques are appropriate. You need to know what your primary threats are. So I work on an e-commerce site. So my web servers are in the public, obviously behind firewalls, DMZs, web application firewalls, security tested, etc. But I do need to allow web traffic to reach my web servers. So the risk there is all the things I've listed and then some. So when I think about threats, I worry about in transit. So we're going to talk about HTTPS. You should be using HTTPS regardless of what your site is. People could access my config file. So if they did honestly take control of my web server and gain admin rights, they would be able to read any of my files. They could do a dump of memory. And if they did that, they would be able to capture anything that is stored in variables, but not yet garbage collected. So things like passwords and things that happen to be in memory or credit card numbers could potentially be found that way. I assume they can modify my pages. So they could change my code and run different code on my servers with the privileges those servers have. They could also reverse engineer assemblies. So if you've done that before, you do a build, you have a DLL, an assembly, you can use things like ILDASM and basically see things like string variables and such. So we'll talk about storing things, but those are all the things that I worry about. Obviously for me, the only really secure thing I could do with my web servers is to shut them off, right? Put them in a corner. I can't do that, right? I need to have the risk versus rewards. I just need to think through what are the ways people would attack me so I can have the right kinds of protection in place. I have company security policies, so it's very likely that your company has rules about how you need to do security, how you need to use cryptography, so you need to pay attention to that. There's regulatory compliance. So we take credit cards, so I have to be PCI compliant. That brings a lot of rules in as far as how we handle sensitive data. And I want to have layered defenses. And again, how much is enough, right? So if you think of a funnel, I'm going to show you practical ways to use cryptography. And if I didn't do anything, how people could attack it. And then as I add more layers, how it increases the difficulty. So it cuts down the number of people that would be capable of launching those kinds of attacks. If you don't take anything else from this talk, please don't write your own cryptography. So I've run into developers that know that their language or framework has cryptography built in, but they think that if they wrote their own algorithm, people would not be familiar with it, so it's going to be more secure. I know a lot of really good cryptographers that have made mistakes. So they do their own implementations and they've done very good stuff in the past, but they do slip up somewhere. So you really need to, if you want to write cryptography, you'd really need to be in that community so you can have people doing peer reviews and such. So please don't write your own. This stuff is available to you. It's vetted, tested. Take advantage of that. I want to mention the .NET algorithms and how they're implemented just because this wasn't very obvious when I first started. So when you look at classes, there will be some suffixes. Things like managed. If it ends in managed, that means it's written in most likely C#. So if it has a CNG, that means it's just a very thin wrapper for the crypto next generation available on newer Windows platforms. If it's crypto service provider, that means it's wrapping crypto API, which is on older Windows systems. So in the .NET full framework, these suffixes do just what I said. If you're doing .NET Core, .NET 6, all of these suffix classes were changed. They just wrap operating system libraries. So again, I'll give you an example. If I were doing government work for the US and I needed to be FIPS compliant, I could not use AES managed, for instance, because the managed implementations have never been FIPS certified. So again, if you're doing .NET Framework, these things matter. If you're doing anything .NET Core, .NET 6, etc., they'll just wrap OS libraries. So all of them are equivalent essentially, and I'll show you examples of that throughout the code. The last thing to be aware of if you're doing cross-platform work, make sure you check out that bottom URL because you can create something using the cryptography libraries in .NET. And I'm a Windows developer, so it might work fine while I do my testing on Windows. I go to deploy to Linux and it may turn out that that feature is not available. So it's building just fine, but as I deploy it and run it, it'll say that's not available. I don't want to be in the situation where I'm testing in one place, assuming it's going to run on another platform, and it won't. So if you follow up on that, you can see which features and classes are available on each platform. So let's jump into techniques. So the first one we're going to talk about is hash functions. So the idea with a hash function, it's what's called a one-way function. So it's very easy to compute, but it's hard, hopefully impossible, to reverse. So if we look at the diagram, I've got some text on the left-hand side here. When I compute the hash, I'm going to get a fixed size result on the right-hand side. The length of this is dependent on which particular hash algorithm I choose. But no matter how big the text is on the left, it will always be that fixed size on the right. It creates what you call a data fingerprint or a digest, and we're going to use it for both integrity and for authentication. Those are the goals that this applies to. In .NET, there's a base class called hash algorithm, and there's a number of specific classes underneath that. I listed some of them here, but I struck them out if you shouldn't be using them anymore. So MD5 was broken a while ago. SHA-1 has been broken more recently. So those are things that you should not be using on production systems because they have known flaws at this point. PCI a few years ago started saying you could not use SHA-1 algorithms anymore. In .NET, there is the SHA-2 family, and you can see the specific classes in there. SHA-256, 384, and 512. That's just the number of bits in the hash result. There is actually a SHA-3 family of algorithms. So in the US, NIST ran a contest and said we need to come up with another type of hashing algorithm that's different than how SHA-2 is implemented. In case SHA-2 ever gets broken, we want to have an algorithm already ready for people to use. So that's already been done. They chose an algorithm for that. The bad news for us is it's not yet implemented in .NET. So that's why I don't list it here. I personally, because of my own philosophy and company regulations, I'm not going to use a third-party implementation of SHA-3 that I find somewhere online. I'm going to wait till it's available in .NET. SHA-2 is still considered secure, SHA-3 is just there for the future in case something happens to SHA-2. There are also keyed hash algorithms. So I'm going to show you an example of the HMAC and why you would want to sometimes use a keyed hash algorithm rather than a normal hash algorithm. So let's go over and take a look at what hashing looks like. So I've got a string here up on top, and it hashes to this result. And that just happens to be a hex representation of the hash value. So let's see what that looks like in code. So here's the code for that. I've got start with a string. So the first thing we'll learn about .NET cryptography, we all like to use strings. The library wants to use byte arrays. So we're going to have to do some conversions as we go. So here's my text that I want to compute a hash of. Here's the way to do it in .NET 6. I'm just using SHA-512 and say I want to create an instance of that class. You can see I left in comments here the managed and the crypto service provider suffixes. You could have used those, you still can. Now that they are meaningless in .NET 6, they all wrap the same thing. I just choose to use the main class. On this line, we'll see I've got my plain text string. I need to convert that into a byte array. So this will be a familiar pattern we'll see throughout the talk. There's a lot of ways to take a string and make it a byte array. I chose to use UTF-8. If this is just for my system, it really doesn't matter what I pick. In other words, if I'm the one using it, decrypting, encrypting, and I'm not working with a partner, it doesn't really matter what I pick. If I do work with a partner, you're going to want to make sure that you're using the same encoding technique. So this encoding UTF-8 get bytes just changes my string into a byte array. And then I'm allowed to compute the hash, and I get back a byte array with the hash result. Next, I want to show that on the web page. So I need to take it out of a byte array, put it back into a string. So there's a number of different ways to do this. As I said, I chose to use hex, and there's some reasons that we'll get into as we progress in the talk. But basically, each one of the bytes is represented by 2 hex characters separated by a dash. So that comes from the bit converter class. So I just say change that byte array to a string and replace the dashes. And that's how we got the resulting look like this. That is just a hex value. If I were to come back in here and if I uncommented out this longer string, like I said, my hash result will still be the same size because it's dependent on the algorithm I picked, which was SHA-512. It's going to be 512 bits, regardless of how large the input is. Okay. So that is hashing. As I said, we'll talk about the conversions and the encoding throughout the talk, but that's a basic example. And again, that's not a lot of code. This is built into .NET, and it's pretty straightforward to apply. So what's a good way to take advantage of something like this? So I want to do what I call tamper-proof query strings. So if you've ever been to a website, you look at the URL and it says customer number equals 123, for instance, you don't want anybody to be able to go there and say there's probably a customer 124. And if they were to change the URL, they might be able to see data for someone else. That would be a problem. So our goal is we want to protect the integrity of the query string. In other words, I'll show you in my example, I don't care if you see the values. I just don't want you to be able to modify the query string. So I'm going to protect it using a hash-based message authentication code, an HMAC, which is a keyed hash. So what I'll do is I'll take the original query string on the server. I'm going to compute the hash of that. I'm going to append it on the end of the query string. Then when it goes to the client, when you come back and follow that link, I'm going to peel off the query string, hash it again, and compare what you just sent hash to what I had sent previously. And if they don't match, I'm going to complain. So let's take a look at an example. So here I have my link. If I click it, I'm going to go up to the query string here. So here I've got A equals 1, B equals 2, C equals 3. So again, it's not confidentiality I care about. I don't care if you see what those values are. What I don't want you to be able to do is come and change A1 to B2 and hit enter and see something else that I may not have wanted you to see. So by default, it worked fine. just showed you a equals 1 because it hadn't been tampered with. If I try to change this to a equals 2, now we get what we want. So it's my first warning. You're not going to do this in production, right? You're not going to show detailed error messages to hackers or even customers. Customers don't want to see this. It's going to scare them. We don't want to show hackers this because we're explaining to them hash values don't match. That helps them attack your site. So in production, we would have a generic page. Since I'm doing a demo for you here, I want you to be able to see what these errors are. So it did what I wanted it to do, right? I stopped you from being able to modify the query string and be able to see anything. So now we start thinking about what would an attacker do. So let's look quick at the code and then we'll come back and see how to attack it. So here's my setup tamper proof. So the first thing you'll notice, I can't just use markup to create links anymore. I can't have an A href equals with all that stuff on it because I need to do a computation of that hash. So that is the query string value I wanted. I just wrote a library. So this is a pretty typical thing your company would do. They don't want you to each implement hashing. They would have a hashing class probably with a compute hash. If I go to that definition, it lets you choose a couple things, the output, whether you want to use a key or not. In this case, I'm going to use a key. So if I didn't use a key, we just would use the same algorithm we did before. Because I asked to use a key, it's going to use this HMAC. Here's your other warning. This is a secret key that's not so secret the way I have it here. Again, for the demo, I've got it pasted here. We'll talk about key storage later, but I wanted you to be able to use this in demo code. So this is my key. And then I do the same compute hash that I did before with UTF-8 encoding. So all of this stuff is pretty similar. And then I allow you to output it as either hex or base 64. So let's see what this, how somebody would try to attack this. So think about other things they might do, right? They might try to just delete the hash. Still doesn't work. If they were looking at this closely, hackers, it's not going to take them very long to realize that this looks like it might be using hash protection. So they can come out here and look at the length of this and figure out that it's a 512-bit hash. So that what they could do, they have access to the same libraries I have. So if we go into this hack tamper proof, they could compute a hash just like I do, but use a equals 2, right? Would this work? Let's go back and hit our page. So I'm going to go hack tamper proof. So that's the hash value if it had a value of 2. So I'm going to go back. I'm going to try to change this to a 2. I'm going to try to change the original hash to the new, and I'm going to hit enter. And it still doesn't work. So this would be kind of curious for a hacker. They see I use hashing, they computed hash. Why couldn't they do this? We're back to our layered defenses. The thing that I have that they don't have still is this secret key. So we talked about the funnel before, right? If I didn't have any protection, anyone in the world, well, some people won't figure it out, right? A certain level of people will see URLs and never touch them. The next level would be, oh, I see a customer number. I'm going to go change that and see what happens. Then if we start adding hashing, that's going to eliminate a whole set of people that can't just go modify it. They have to understand a little bit about how hashing might work. We've made it that much harder. So now this person has to be able to not only understand all of that, but they have to be able to break into my server and gain access to this key. It's possible, right? I talked about if this were my public web server, somebody could, if they found out how, potentially gain access to the entire server. But the number of people that can do that is much, much less than if I didn't use keys and if I didn't use hashing, if that makes sense. This is a good example of layered defenses. Another place we use hashing is passwords. So it was considered a best practice for passwords. The technique is, I'll show you some variants of it. It's used for authentication. So I did research when I was in college many years ago on password cracking. And I was doing it on Unix. And when they designed the Unix operating system, the designers looked and said, you know, how are we going to protect passwords? They looked at hashing and they found it very intriguing because they said, you know, if we took your password and hashed it and we stored that in our password file, that can't be reversed. So if it's a good hash function, you can't take the hash value and get back to the original password. So they said, that's great. So what we'll do is we'll take your password, we'll hash it, we'll put that in. It was called the Ecb password file. And they were so confident they did it right that they said, we're going to make that file be readable by anybody who has an account on this system. So what people would do, what the attackers did, is they might have a low-level account on a system, or someone gave them a password file for a system. They wouldn't try to reverse the hash because that shouldn't be possible if it's a good hash algorithm. But what they can do is they can take a whole bunch of guesses of what the password might be and pre-compute the hash of all of those guesses. So back in the day, people would take an online dictionary and they would hash every word in the dictionary. So they had Apple and they had what that hashed to. Now what they can do is look in the password file and see, do any of the hashes match? And if they do, they can come back and figure out what the original word was. And back when I did that research, it was about 60 or 80% of passwords came from a dictionary. So let's take a look at what that looks like. So I'm showing a very stripped down example. I'm just creating a dictionary that has some words that I think you might have used for a password and their hash values. Then I went into the password file and I took somebody's hashed passwords, and then I just used this crack password. It just tries to see, does that hash show up in the dictionary? And if so, what's the actual original word? So if we go run this, we'll see the original word happened to be secret. So I haven't broken the hash algorithm. When they did this, they didn't think through how somebody would attack them. So if the words happen to be simple words or in a dictionary, or today you can actually get password lists. So you can get lists of the most common passwords. So a hacker will just hash all of those passwords. And if it's any of those, they'll be able to crack it. Let's look at what people did for defense for this. So for defense, they said, well, that's a problem. Why don't we add what's called SALT? So they said, we're going to take every user, we're going to generate some random data for that user and call it SALT. When you give us your password, we'll take your password, your unique SALT. We'll hash those two together. We'll put them both into the password file. So what that's done is it's made it where it's really hard for a hacker to mount an attack against the entire password file, because now they can't just pre-compute the whole dictionary. They have to pre-compute the whole dictionary using your specific SALT, if that makes sense. So the good news is that it made it really hard for a hacker to attack an entire password file, but they didn't make it any harder to get an individual password. Because if I were doing it, I'd take the password file, I would use the hash password for the administrator, and I would pre-compute using their SALT. So again, it was better when we talk about layered defenses, but it still isn't perfect. Let's look at what that would look like. So here I have some data I'm going to hash. This is some random SALT. We'll talk about random data in a bit. The rest of this should look the same. I'm just going to compute a hash. And I compute it with both the password and the SALT. And I get back a value, so I'll show you what these look like. So the first one is just a normal, here's hello world, here's the SALT. This is the default hash. This is the one when I have my own unique SALT. To add one more layer of difficulty, people will also do this. So not only do they take the data, the password, and the person's SALT, but they also use some other secret random data that they store on the server. So again, talking about layered defenses, now you would have to be able to conquer this page and gain access to my secret SALT. Again, I wouldn't have it right here in the source code. Wherever I have that stored, you'd have to be able to break into the web server and get that before you could pre-compute all the words that you wanted to use. So that's what they did with salting. And by the way, nowadays it's so much easier to attack because back then I would use a dictionary. Today with everybody's social media, I know spouse's name, kid's name, your cars, everything about probably your birth year, your birth date potentially, because everybody's saying happy birthday to you. I've got all of this data I can use to make guesses at what your passwords might be. So what do real systems do today for passwords? So if they're storing things, you've probably heard of things like bcrypt, or in .NET, it's PBKDF2. What these functions do, they are hash functions, but they're built to have what's called a work factor. And so it's easier to show this one in code. So I'm a Led Zeppelin fan. No, that's not my password, but imagine that were a password. I've got some salt. You create that class, but here's the magic, the iteration count. So rather than just run a single hash, I'm going to run a hash over and over again, in this case, 100,000 times. Why am I doing that? I'm trying to make the computation of the hash be intentionally slow. So if a hacker wanted to go to an online dictionary and pre-compute the hash, I'm going to choose a penalty, so to speak, of what that will hurt them for time. So I will go to my current hardware and I will figure out, first I'll choose my penalty. So in my case, let's say it's a half a second. I'm willing to slow up a normal customer logging in by half a second. If I do that, then I'm making each hash the hacker tries take half of a second. So just to compute the entire dictionary is going to take them a really long time. And that's the idea of how these things work. So again, I chose a half second, and then I just ran it on my hardware to find out how many iterations will it take to get to about a half a second. This is a 101 talk, but if you are going to use this kind of technique, just be aware that someday you're going to have to make this be a bigger number. And when you do that, your hash values are going to change. So you're going to have some strategy in place about, are they using the old count or the new count, and get transitions and stuff in place. But people who are doing password storage today, these are the kind of techniques they're using. They're making it intentionally hard from a time standpoint. And there's also ones that are memory hard. In other words, there are things that intentionally use a lot of memory as well. So there's algorithms that do that. So again, the idea is just make it hard for the attacker to pre-compute a whole bunch of different hash values.
Hey, Robert, we have a question.
Sure.
So Sean asked, I've seen some systems where the user's salt is stored in the same database in the same row as the hash password. Is that typical?
That's typical, yes. And that's what they did with the password file too. They store that salt right in the same row that you have the hashed password, because when you come back and you type in your password, I do have to locate your salt. So I need to be able to get your salt. And so most people put it in the same row. You could try trickery and put that somewhere else, but you do need to have the salt for that individual user stored somewhere. And it's pretty typical they'll put it in the same row, or in the case of the password file, the same line in a text file. So that's pretty typical. Okay. The other flaw that I mentioned was, don't make your password file readable to anybody on your system, right? I mean, that's something you wouldn't normally do today. In other words, the account that has access to the rows where the user IDs and passwords and salt and stuff is stored should be locked down to specific users. So that was their other flaw, is they were just so confident the way hashing worked that they said anybody can read the file, we don't care, which turned out not to be a very good idea. So we're through hashing. Now we're going to get into encryption, and there are standard terms for things in the industry that I just wanted to go over. So the first one is plain text. So that's just my original data. Encryption is the process of obscuring that data. Once it's encrypted, it's called ciphertext. And then when I do decryption, I'm going to take the ciphertext back to the original plain text. And then Cipher is the name for the algorithm I use to perform the encryption and decryption. So we're about to get into what people normally think about with cryptography. It's encryption, and it's used for confidentiality. So I don't want people to be able to see this data. There's two high-level techniques, or I guess ways to create these algorithms. The first one's called a symmetric algorithm. So I'm going to go to the picture here. So I have plain text that I'm going to encrypt with a secret key, and I have my ciphertext. Whoever's going to decrypt it will use the same secret key. That's why they call it symmetric, because the same secret key is used for both encryption and decryption. And once it's decrypted, you get back to the original plain text. So this is a symmetric algorithm because the key is used, same key is used for both encryption and decryption. So I'm going to talk about, there's Symmetric Algorithm is the base class in .NET. I'm going to focus on AES. It's by far the most popular, still considered secure encryption technique. DES has been broken for a long time, and triple DES is either broken or very close. So I'm going to focus on AES. So in .NET, the symmetric algorithms are called block ciphers. So what that means is it takes your message and it's going to break it into individual blocks, and it's going to encrypt a block at a time. If you think about how your message is set up, it's very unlikely that by the time I get to the end that it will automatically fill a complete block. So there has to be some sort of padding at the end for that last block that's not full. There's a couple different ways to do it. I'm going to show you, pick this one because it adds the most randomness. We'll see why you don't want to use zeros specifically. There are a lot of different modes for AES. The first one's called Ecb. And what that one does is it says, I'm going to take the first block, I'm going to encrypt it and get ciphertext, and then I'm just going to move to the next block and encrypt that. So each block is just done individually. And the problem with that one is that if you ever have two blocks that have the same plain text, they're going to have the same ciphertext. And so a good visual way of understanding why that's a problem, they have what's called the Ecb Penguin. So on the left-hand side, I have this image of a penguin. If I were to use Ecb mode, every one of these pixels will be encrypted, but they're all encrypted to the same value. In other words, all of these white pixels become some other value, but it's the same value. Same with all the different colors. So you can see if you use Ecb mode, it is encrypted here, but I can still get the general shape of it's a penguin. And that's because every block is just treated individually, and that's the flaw. I'll show you why you don't want to use that in practice here in a moment. One of the most popular modes is CBC. So I'm going to show that example. What CBC says is it says I'm going to encrypt the first block. I'm going to get ciphertext. I'm going to use that ciphertext as input, so it's getting some random input when it encrypts the next block. So in cryptography, the more randomness we can add, the better. So it's constantly using the previous block's ciphertext as some of its input when it encrypts the next block. That way, even if the two blocks of plain text were the same, they're going to end up being encrypted differently. So when you think about that, where do they get the random data for the first block? That's what's called the initialization vector. So the initialization vector is just random data that's used to seed the first block. So the way it works, it does not need to be a secret. It just turns out from the way the algorithms work, you don't have to make that be secret. You're going to create ciphertext and an initialization vector. You give that to someone else, they'll be able to decrypt. What you don't want to do with an initialization vector, don't ever reuse it. Anytime you're reusing an initialization vector, you lose some of your randomness. So that's what's important about that one. So let's take a look at what the code would look like. So I'm just going to type, let's do test. I'll encrypt it. So what you'll notice, I'm using CBC mode. So every time I do an encryption, it generates a random initialization vector and therefore gives me different ciphertext. So even though this was the same message, every time I'm encrypting it, it looks different. So an attacker doesn't learn any patterns. They can't tell that they've seen this encrypted data before. And then I'm able to decrypt it. So let's see what the code looks like for that. So I'm using Razor Pages, by the way. I'm not going to spend any time on the web part of this because it doesn't matter. When I click on the encrypt, it comes into this method. So the first thing I want to do, I've got both an encrypt and decrypt that want an AES cipher. So I just wrote a common function to create one. So again, here I'm just using the base AES class. Like I said, you could do managed or crypto service provider. I'm doing .NET 6, so that doesn't help me in any way. It lists the defaults up here. So I'm going to change the padding to be the more random padding. Here is my super secret symmetric key. Again, I would not store that directly in the source, but I need to give it to you for the demos to work. Now I have a cipher created. Every time I create a new instance of AES, it will give me a new initialization vector. So that initialization vector happens to be a byte array. So I want to convert it into a string so that I can show it on the web page. So in this case, I chose just to do the other common encoding, which is called base 64. Base 64 because it typically will end with a couple equals. So I'm just converting that into a string using base 64. So that's my initialization vector. Now I want to actually encrypt the data. So here I create the encryptor. This is what we were doing when you saw hashing. We need to change the plain text string into a byte array because all of the cryptographic libraries want to work on byte arrays. And then this is the line that does the actual encryption. And then I chose to base 64 the ciphertext. I could show it on the screen. So the important things to notice here, not a lot of code. AES is still considered secure. It's a trusted algorithm. .NET has had a lot of reviews, a lot of people testing, vetting it. So not a lot of code. Again, why you don't want to write your own. If I were writing for a company, I would make a library available to the rest of the developers where I could just pass, here's the key to use, here's the data. It would give you back the ciphertext and the initialization vector, so it would be even simpler to use than this. But that's the basic example of how you would do AES encryption. So one of the questions, how do you create a key like this? Well, it needs to be a random key. So in the code, I gave you this get bytes page. So let's look at what that does. It's just going to create a key that's the proper size I want. And I'm using AES 256-bit. So every time I'm hitting refresh here, it's just creating a new random key for me to use, represented in hex. So this was the only thing that changed. I built this into .NET 6 over the weekend, and I noticed the squiggle here. If you know, random number functions and libraries in most languages aren't really very random at all. And that's true of .NET too. If I were to use just the random class, it's not actually very random. You need to use what's called a cryptographically strong random number generator. So up until now, that has been this RNG crypto service provider. If I were to hover or if I look in the build, they are giving me a message that this is now considered obsolete. There's a new random number generator class that's also cryptographically strong that I should be using instead. So I'm going to make that conversion at some point. But this basically creates a set of random data, 256 bits, and then converts it into hex so that I can use it in the rest of my classes. So if you think about randomness, computers, even the cryptographically strong, are not great at randomness. So if you're familiar with Cloudflare, so they're a major internet CDN and internet provider, they actually have a wall out in California that's all a bunch of lava lamps. And so what they do is when they need random data, they actually take a picture of the current state of the lava lamps and digitize that. So that's part of the random data they use to help them create more random keys because they're reaching outside of computers where they can get some true randomness off of this lava lamp current configuration, which is kind of cool. So we talked about symmetric. It's cool because it's really fast. If you think about it though, if I were to go into the chat room here or the participants and I found one of you and said, I want to send you a secret right now, I would have a problem, right? I could use a symmetric algorithm, but in order to send you the secret stuff I want to send, I need to send you a secret key, and I'm right back where I started. I have no good way to send you something secret. So what they came up with instead of symmetric is asymmetric algorithms. So when you do asymmetric, each person that participates will create a public-private key pair. Obviously, the private, they don't want anyone else to see. The public one, they'll give to other people. So let's look at how these work. I take plain text. I'm going to encrypt it using the receiver's public key. So whoever I'm sending to, I'm going to get their public key. I'm going to encrypt it. Now I have ciphertext. I cannot even decrypt it anymore. So there's no way I can decrypt it. The only thing that will decrypt it is the receiver's private key. So they're going to keep that on their own internal system. They're going to be very careful that it's not stolen. they use their private key to decrypt it, and they get back to the original plain text. So that's great. I'll say this carefully. It doesn't make the key distribution problem go away. It just makes it a lot easier. So can I take your public key out of your email signature and trust it? I wouldn't, right? Email's like a postcard. Anybody could change that. Would I trust your public key on your LinkedIn profile or Twitter or some site that uses HTTPS? Probably. So it doesn't make the key distribution problem totally go away. It just does make it where I can see your public key, but I still have to trust that I got the right public key, right? The bad news about these algorithms, they're about 1,000 times slower. So they're an order of magnitude slower than symmetric algorithms. And they also cannot encrypt large amounts of data. So we're going to talk about what we do about that in a bit. But there's a number of classes in .NET. I'm going to focus on RSA. So let's take a look at what that would look like. So here I'm going to type test again, do the encryption. So here's my ciphertext, and then I can do a decrypt and get back to the original. Let's take a look at what that code looks like. So again, I have an encrypt method. I want to create a cipher. So I just created this general cipher. I took the receiver's public key and just put it in here for the demo. For real life, I'd probably have a database of all the people I want to send to along with their public keys. So I will create an RSA cipher and I will read in the public key to use for this encryption. Now I'm going to do in the encryption, I create the cipher. I got to do the same stuff I did before. I need to take the string and convert it into a byte array. Then I will do the actual encryption. One note, please use this for padding with RSA. The default is no longer considered secure. And then I'll do base 64 and get back to ciphertext. So again, if you just look at this quickly, that's not a lot of code to do asymmetric encryption using .NET and trusted RSA classes. So where would I use this? So a practical example. So let's say I have a website that takes credit cards. I want to take your credit card number. I'd like to encrypt it. I can't use hashing again, right? Because I wouldn't be able to get the credit card number back. I want to use encryption. So I have two choices. I could use symmetric or I could use asymmetric. If I pick symmetric, that means it's a secret key. So I would have to store the secret key on my web server so that I could encrypt it. My problem with that is, I told you earlier, I treat my web server like it could be compromised. So I really don't want to put a secret key on my web server. I could, however, do asymmetric. I could generate an RSA key pair. I could put the public key on my front-end web server and keep the private key internal on a very secure system behind a bunch of firewalls. The only time that needs to get used is before we talk to the credit card processor, we need to get the number back. So I could keep that internal. Again, this is meant for small amounts of data, which for a credit card would be fine. So let's look at what that code would look like. So I'm going to type my super secret credit card number. As soon as I do that encryption with that public key, now the only thing that can decrypt it is the private key. And that's going to be somewhere very secure inside my company. So what I would do, I could put that in a database table wherever I want to put it. Then internally, that system that needs to talk to the credit card processor would get it and could get back to the original number. Okay. So with that, it would be a good example of using the right type of encryption for the situation. So today, a lot of credit card processors will actually create a public private key pair for each company, each customer they have. They'll keep the private key themselves and only give you the public key. So now when you put that on your web servers, as soon as you do that encryption and store it, essentially now your own company can't even decrypt it. You're just going to send it over to the processor. They're the ones who have the private key. They'll be able to pull out the credit card number and do the authorization. So that's a pretty typical way to approach reducing risk today using this sort of a concept. Okay, So now that we've got through the hashing and encryption, we're going to talk about digital signatures. So the idea with the digital signature is we want integrity. So we want to make sure that if I were to, let's imagine I have a contract that we're going to agree to, you want me to sign it and send it to you. You want to make sure when I send it to you that no one's tampered with the wording of the contract. And you also want the non-repudiation. You want to know that you can prove I was the one who signed it, right? Just like normal signatures, you could compare two signatures. You want to be able to prove that I was the one who signed this digital document. So in order to do that, we will hash the contents of the message, right? Hashing gives us integrity, and we will sign it with the sender's private key. So let's look at this little picture. So to make it one more level difficult, you don't need to do confidentiality with digital signatures. In my case, I'm just going to pretend that I want to send you a contract that I also don't want anybody else to be able to read. So to do that, let's look at the diagram. There'll be lots of familiar parts here. So I take the plain text and the receiver's public key and do the encryption. We saw that before. That's just asymmetric encryption. We get back ciphertext. We'll compute a hash based on that ciphertext and get a hash value. So now that hash value will prove that the ciphertext has not been tampered with. The digital signature part is I will encrypt that hash with my private key. So I'm the sender in this case. When I do the private key, so the public and private keys are just inverses of each other. So if I encrypt it using my private key, anybody who has my public key will be able to verify my signature. So by the time I'm done with this, I'm going to have ciphertext to send and also a signature. So let's look at what that would look like. So I've got a fictional web page here that wants to send a credit card maybe to another partner on a URL. So if we click it here, you'll see in the URL that there's a secret being sent. And here's the confidential data. And if I were to go more to the right, I also have a signature, and that has the digital signature. Take a look at what the code would look like. We'll just look at the sender here. So in order to do the encryption, I need the receiver's public key, and I need my public and private. I'm actually just going to use my private in this case. So there's ways in .NET. I've got classes in here to let you create RSA key pairs and containers and such. And they're just XML. So again, I wouldn't be storing this directly in my source code like this, other than it's a demo. So now what I want to do the signature, I'm going to create a cipher, and I want to use my private key. That's what I'm going to use as the sender. I'm going to create a receiver cipher using the receiver's public key. That's my super secret credit card number. I'm going to change that string into a byte array. We've seen that before. I'm going to use the asymmetric RSA encryption. That's what's right here. So I've encrypted it. So now it's ciphertext, so I have confidentiality. We know how to compute hashes already, so I'm going to compute a hash of it. I'm going to use that for integrity to make sure that the data has not been modified. And then here's the different part. I'm going to use this .NET class that applies a signature. I'm going to tell it to use SHA-512. And right here, it creates the signature. And then I just choose to use base64 encoding. And because I'm putting it on a URL, if I use base64 encoding, I also want to use URL encode so that they're safe characters to use on a URL. That's why earlier I was using hex. You can use whatever you want as long as you agree with your partner. But this just shows you if I use base64, I might have to URL encode it. And then that gets tacked on to the URL as we saw. Okay. So that is digital signatures. So another example of kind of this, they call it hybrid encryption, where we're using all of these techniques together, is HTTPS. So if you're providing a website today, you should be using HTTPS to secure it. So when you create your website, I'm the server. I'm going to create a public-private key pair for my server. I'm going to take the public key and go out to a certificate authority. So there's lots of certificate authorities. One of them called Let's Encrypt is free now, and it's automated, and I've used it. It works pretty well. So as the provider of the website, I create my public-private key. I take the public key. I go to Let's Encrypt. Let's Encrypt is going to want me to prove that I own this domain and this website. So there's various ways to do that. They might have me drop a file in the root folder, or they might have me add something to the DNS entry. However that process works, I prove to the certificate authority that this is my website. They then digitally sign my public key and my business name and some other stuff into what becomes the certificate. So the way it works, browsers know the well-known certificate authorities like Let's Encrypt, so they will trust certificates that are signed by these well-known certificate authorities. So if we walk through what really happens when you visit a website, there's what's called the TLS. So HTTPS is just really the HTTP protocol running on top of an encrypted channel. And today that should be TLS. So the browser will go to the server, and they do this handshake. So the browser goes into the server and asks for the server's certificate. When they get that server certificate, they know the well-known certificate authorities. They have the public keys for those certificate authorities, so they can prove that Let's Encrypt signed the certificate and it hasn't been tampered with. So I can trust the server's public key. So now I have a public key for asymmetric. I don't want to encrypt all of my data using that because I know that's really slow. So the browser is going to generate a random symmetric key. It will encrypt that symmetric key using the server's public key and send it to the server. So now what we've done, the browser got the server's public key, so it could create a random symmetric key and encrypt it and hand it to the server. So now the browser and the server both know a random symmetric key to use for this session. So now they drop down and start doing symmetric encryption because it's really fast. So that's a good example that sees basically all of the things we've talked about, the hashing, the digital signatures, asymmetric and symmetric, how it all comes together to provide what's actually a practical service for everybody who's doing HTTPS on their websites.
Hey, Robert, Kevin asked a question. So he mentioned on a previous slide about the content being small. When does it say, what size content is safe to use with public key crypto?
So in the case of RSA, I thought it was 4096. I would have to look it up again, to be honest with you. It's pretty small. So I mean, credit card sorts of things. In the case of this contract, depending on how big your contract is, it might become too large, and then this would just get more complicated. You would actually create a symmetric key, encrypt that. You know, the same sort of hybrid idea. If you can't use the asymmetric because you can't encrypt that ciphertext, you'd have to make this even more complicated and use symmetric encryption and use their public key to pass it, that symmetric, to them, if that makes sense. But I thought it was 4096 for RSA. If you can't find it, send to me. I'll show my email at the end again, and I'll send you what it is for RSA and .NET. Okay.
Perfect. Thanks, Robert.
Yep. So now we'll talk about key sizes. So in AES, there's a couple different sizes that are standardized. It's either 128-bit or 256-bit. So if you look at your two choices, someone who's going to break AES, if it's implemented correctly, they're going to break it by trying to brute force guess your key. If you look at how long it takes them to brute force 128-bit, 256-bit is not twice as long. It's actually every bit I add makes it exponentially harder, essentially, to do that brute force. So you really want to use long key sizes. So I use the longest I can, which for AES is 256 bits. For RSA, it's 4096. They argue today 128-bit AES is probably good enough. I'm going to err on the side of security. It's a security talk. If you're concerned, your real trade-off is just performance. So do both of them, run your system and your tests, and see. When I've done that, they're relatively close from a performance perspective, that I want to make it really hard to brute force guess my key. So I'm going to go with the maximum sizes for the respective algorithms. Next is key storage. So we talked about key storage is the worst part of cryptography in my mind. If you step back and look at my philosophy, I treat my web servers like they're compromisable, which means that there's nothing I can do on an individual web server that somebody could not own that web server and have access to. So I got around it in my examples by using asymmetric. So I don't have to store a secret key on my web server, right? I'm just going to store a public key. There are, depending on what your framework is, what your deployment environment is, you could look at things like Azure Key Vault and other options. I would say all of them are better, obviously, than storing it in my config file or storing it in a string. But all of them also have risks involved with them. That's why for me, with the credit card example, I'm just going to do the asymmetric public key if I can, because I don't want to try to store a secret on a web server. If that makes sense. Other than that, you're going to have to look at your individual environment. Again, it's a 101 talk. There's a lot of different thoughts and procedures and protocols to try to do key storage successfully. But like I said, it's the worst thing in my mind for cryptography today is how do you store that on a machine you know can be compromised. So in summary, don't write your own cryptography. If you take nothing else, you saw the algorithms are available in .NET. They're available in other languages. So just find trusted implementations that have been vetted by security people. Know what your goals are. So use hashing if you're trying to validate integrity of data or to prove that you both know the same secret for authentication. In general, you want to use symmetric algorithms because they're so much faster, unless you have special needs for asymmetric, like the digital signatures, the key exchange. And it's important to know your threats and choose proper countermeasures. So I did a capture the flag competition last year, and I did it again a few weeks ago. And I'd studied security. I've been involved in security audits. I understand conceptually SQL injection and everything else. It's really a different world when you do it in a controlled environment and you can actually see how our attackers working around things. I did some pretty unique approaches to breaking things, even very unconventional things to get the flags I needed, because hackers don't follow rules, right? They're going to find a way to break into what you have. So just think about how would somebody attack this, know what your threats are, and make sure you've got the proper countermeasures in place. I do have a Pluralsight course, Introduction to Cryptography. It goes into a lot of the history of cryptography. It is using .NET full framework. It's about 2 hours long, so if you're interested in that, you can check that out. All the books in the middle here get into a lot of details about the algorithms we talked about. The first one, the Practical Cryptography in Python. The reason I like that, I don't know Python, and it didn't matter. I used it because they had a lot of good real-world examples of why is MD5 broken? They go into all the things that make up a secure hash algorithm, and they spelled out what is exactly broken about MD5, what's broken about SHA-1, why shouldn't you use those? So I thought that was a good book. If you really want to know all the bit shifting and the math, you can go these next 3. I've read them, not because I care. I'm not that much into the mathematical stuff about how AES actually works. But each of those books also cover how do you use AES securely. So not how it works inside, but how do you use it properly. So that's how I use those books. I like cryptography as a professional, but I also think it's cool from a hobby standpoint. So these bottom 2 books go into the history, like how did the Caesar cipher start? And then it goes into kind of the battle between cryptographers and cryptanalysis people, where you're doing that. They break it. What do you put as the next layer? They break that. I like reading a lot of that history. And so those are good books. They talk about how Enigma was broken, lots of other ciphers, what their flaws were that people were able to break into. So it gives you a good perspective on how people might attack you. That's my Twitter, my email, and my blog. And that's a link to the slides and the code. Again, it's the slides, and then it's .NET 4.8. And then what I showed tonight, .NET 6. And with that, if we have any other specific questions, we could go through those.
Kevin asked, have you followed any of the quantum computing threats to cryptography? Any thoughts on that?
So I have. So quantum computers, the risk of it is specifically mostly around the asymmetric So I talked about RSA. There's also elliptical curve and other asymmetric algorithms. And the problem with those is they're all based on math that's really hard to do today. So like RSA is based on factoring large numbers into prime numbers is very difficult from a mathematical standpoint. That's what makes it hard to break RSA. In the quantum world, the risk will be that that math might become simple, in which case specifically the asymmetric algorithms might all become broken. And so it's worth keeping an eye on quantum. I've read some of the arguments about what people think will happen. They think cryptography will get new techniques, you know, I'll assume we're on the good team, protecting data. The good team is trying to protect stuff. Once quantum makes it where the bad side will have an easier way to do refactoring, the good team's going to have to come up with unique ways to use quantum computers to make it computationally difficult again, so that attackers can't break that. But it's a risk today. I would say at the current point, we've got the best that we've got, right? I mean, when quantum becomes practical, there's going to have to be different approaches specifically for asymmetric more than anything else. So I don't know if that answers it well, but it's certainly the risk because the math that underpins all of asymmetric will be easily done on quantum computers is the theory.
If you have any other questions, feel free to speak up now. Why is asymmetric 1,000 times slower? Is it something fundamental with technology or something specific to the algorithms? Asked Sean.
It's the algorithms, just how they're implemented and all the mathematics involved just make them that much slower on today's hardware. So it's just something innate about all that mathematical computation stuff just makes it that much slower. It's not that the specific implementation, for instance, in .NET is just poor. It's just true about the techniques they use and the math they use on current computing systems is just that much slower than things like AES, because AES has been built into a lot of hardware even. So it's been really optimized for being able to perform well. And the mathematical stuff just doesn't fit on top of our current computing architectures as well. So it's just innately that much slower.
Anybody else have any other questions?
And if you do, after you look at the code, feel free to reach out to me on Twitter or email, and I can answer any questions you have as well.
Yeah, well, thank you so much for your time tonight, Robert. This is a great presentation. I'm going to end the recording right now. And as